All right, to get percent water, what we would do, percent H2O by mass, we take just the water, 54, divided by the total mass of the whole thing. 148 plus 54, what's that? 202 times 100, and what do we get? 26?
Yeah.
0.7%. There we go. And that's how we do hydrate problems. I'm only doing that one. I think it's pretty easy. I think percent composition is a home run every time. So I hope we have multiple questions this year. I hope there's a gram formula mass question this year. I hope there's a percent composition formula or percent composition question. I hope there's a hydrate question, because these things I don't think are that hard compared to some of the stuff we've learned and some of the stuff we will learn. All right. So hopefully you're with me on that. You think it's not that hard as well. Do that worksheet for tomorrow. It's just this. Okay. There is a question on the back of that worksheet that is a Regents question where they give you the masses as if you're doing a lab. That's why I do the demonstration with you, so you have an idea that in real life you have real numbers. You don't use the chart numbers, you use the ones from scales. But it's the same concept. Part over whole times 100. All right. Now, these two solutions I just made up really quick. I still gotta let that cool down before we move forward. We're moving on to concentration now. So I teach all the math stuff kind of at once. So grams to moles, moles to grams. Stoichiometry, percents, percent water, percent composition. Now we have to do molarity and parts per million. Take out your reference tables, please. There's two formulas you need to know, or need to know how to use. They're on the reference table. You don't have to memorize them.
There we go.
Very back of the reference table. I want everybody to see where they are.
Times a million.
Ooh.
You can close that one too if you want.
Times by a million.
Wow.
Yeah, that's fine. I'll fix it. It's a mess. Don't worry about it. All right. So, give me the two formulas. Trevor.
Oh.
Massive solute over massive solute.
Wait, give me, what am I solving for?
Parts per million.
Parts per million, ppm, equals mass of solute
Over massive solution times 1 million.
times a million, right? Yeah. 1 times 10 to the 6 is a million. So, we got to make sure we understand what the difference is between solution and solute. And then, go ahead, Tyler, what's the other one?
Molarity
Right, so capital M.
equals moles of solute over liter of solution.
Okay. Those are the only two equations you need to know. Yes, I'm writing them in our notes. Yes, I know they're on the back of the reference table, but that's okay. All right, the more you see it, the more, hopefully you remember it and understand. These two measurements, parts per million and molarity, are concentration measurements. Concentration is a ratio of the amount of stuff, I say stuff sometimes, not too scientific, but the amount of stuff you have dissolved versus how much water you have. So that's what this little division sign here is. It's what this ratio is all about. Solute is like salt. When you dissolve salt in water, solute is salt. The water is called the solvent. We're going to talk about solutions. That's our next unit. Next week we'll get into that. So I have two solutions here on the table. All right, so I'm going to just show these to Nicole. There you go. Okay. Which one do you think is more concentrated?
The one in your left hand.
No.
So from your perspective, the one on the right or left? From your perspective, which one is more concentrated?
On the right.
Yeah.
It's darker. So you just know that. It's like inherent in your brain just from living life. You know this is going to have more particles in it than this does because it's darker. This is a little bit more transparent. Does that make sense? Yeah. So this would have a higher molarity, higher parts per million. So maybe a molarity of like 5. That's a pretty high molarity actually. Molarity of 12. That's even higher. Okay, parts per million, it might have a parts per million of like 2. That's actually a pretty big number. Parts per million is 2. This would have a molarity of maybe like 0.5 molarity, or a parts per million of like 0.01 parts per million, like a very small parts per million. So these, I just put these together real quick so you had a little visual of what the heck we're talking about. So the darker a solution is, the more concentrated. That means there's more solute dissolved in either the same amount of solution or less solution. I tried to put about the same. I just did it really quick. But if you have more solute in a little bit of solution, then it's going to be really dark. If you have a lot of solute, but you have a massive amount of a solution, then it's probably going to be light like this. So it does depend on the ratio, but let's assume this is kind of staying constant, the amount of water, the solution, right? So this is about 100 milliliters, a little less. If I add more solute, so the top number here, numerator goes up, but the denominator stays the same, then these numbers are going to get bigger. So the point is, the more you dissolve, the higher the concentration. So right now, we could figure out the concentration of like students per desks, okay? Pretty high concentration, although there's not too many empty desks. But if I told everyone to get up and leave, and just Tyler and Elias stay here, concentration would be very low because there'd be a lot of empty desks. So I'm just trying to give you another analogy there. So I need you to understand, one, how to use these equations, but that's actually just for getting questions right on a test. What I really care about is do you understand the concept so you can see it, but let's draw some pictures. So give me two beakers here. Okay, try and put, about the same size beaker, about the same size, same amount of water, or volume of water. Now the beaker on the left, we want it to be concentrated. And then the beaker on the right, we want it to be dilute, which means less concentrated. And we're going to represent, so here's our solvent. This is like water, our solvent. All right, we can, right here, solvent. We want to represent the solute by little dots. Anybody want to come up and show us how we could draw this? Come on up, man. Sorry, Tyler. It's just not your day.
I'm just getting shut down at it. That's all it is. Been shut down all day. Figure it out right now.
I like how she's using blue for the solute. She enjoyed that. All right, very good. Draw something similar in your notes. So dilute, the blue dots here are the solute. That's what's getting dissolved. That could be like salt particles or sugar, whatever dissolves in water. And in this case right here, this purple stuff is called potassium permanganate. So those dots could be potassium permanganate particles. So dilute means only a little bit of solute, a lot of solvent, right? The ratio. But concentrated means lots of solute, so lots of dots. It looks very concentrated, right? So that's what concentration means. It's the ratio between solute and solvent. So let's write that, solute, and then point to one of those dots there, if you can, in your notes, okay? And now I'm going to give you some numbers. So for molarity, a concentrated would be like 12 molar. That's how we say that, a 12 molar solution. That's how we say that. 12 capital M means the molarity is 12, and the way you would say that, if you're just hanging out in chemistry lab and you want to say, Adam, pass the 12 molar hydrochloric acid, please. Okay, like you're at the dinner table. So 12 molar is how we say that. Now over here, dilute might be something like 0.5 molar. 0.5 capital M. That's a small molarity. Now parts per million, I'll make it a little bit more dramatic here. Let's say 10 parts per million. That's pretty concentrated. If the concentration of lead in the Hudson was 10 parts per million, the Hudson would be shut down. No one could go near it, do anything. That would be real bad. Okay, that's a really big number. Okay, it's not. Okay, maybe it's more like a 1, which is still not cool, but so we'll use that 1 as an example here. 1 parts per million. Okay. So the EPA or any agency that's going to come to the Hudson, the Mohawk, or rivers, lakes, streams, even the ocean, you want to measure the concentration of fluoride ions or lead ions or mercury content. They will not use molarity in, I say, real life. Labs, molarity is kind of king, we'll call it. But but in real life measurements, like what you might see on a chart or a scale or in the news, parts per million is what you would use. And I told you guys about when I was pumping gas. That was this class? No.
No.
Last summer I was pumping gas and there was a sign that said, I forget what it said now, but I took a picture of it too. I was all amped up about it. It said something was 2 parts per million in the gas. I was like, parts per million, I teach that. This is real life. So I understood what that meant. Now you guys will understand once you learn parts per million. So that's something you might see in real life. You might see that. You'll have an idea of what that means. Molarity, not so much. Just in labs, maybe in college if you take a science class or something. Okay? So I wanted you to first understand what does the word concentration mean, what does concentrated mean, what does dilute mean, and can you visualize it? That's why I gave you those to look at, and then we drew the picture. Now, if I have time, I'll try and give you one example of how to calculate molarity. We'll start with that one. Tomorrow, we'll finish up with this stuff, and then we're going to move on to solutions, which is the next unit. So I'm thinking next week, Thursday, Friday, you'll have a quiz on all the math stuff. Percent composition, grams to moles, moles to grams, this stuff. Yeah.
What about that stuff in the back?
Oh, totally forgot. We'll end with that. You can pack it up. Oh, so I'm going to add additional homework here. All right. So I want you to calculate the percent water from the sample in class here.
What?
Calculate the percent water. So the initial mass was what?